Check it out now, y'all.
Nano Hub U, online instruction.
Welcome to week 2 of this course, and just to remind you what we did in week 1 is we started with this model of a small device and in terms of how to understand the current flow through it, and we introduced this concept of a density of states that tells you that in a given energy range, how many states do you have per unit energy for electrons to conduct. And as we discussed, current flow depends on electrons going from left to right, making use of these energy channels that are available. And current flows only in the small energy window between the two electrochemical potentials, because this is the range of energies where one contact wants to fill up these levels, the other one wants to empty them, and so electrons keep flowing. And based on this viewpoint, we first obtained an expression for the conductance, which looked like Q squared D divided by 2T, where D is the density of states in this energy level of interest, and T is the time it takes for an electron to get through. And then we said, well, if you have a ballistic conductor where electrons go straight through, then you can write this time as length divided by the velocity, the average velocity. And based on that, we obtained an expression for the ballistic conductance. And I have these 3 things here because that's an average velocity, and the actual average sort of depends on whether we are talking of a one-dimensional conductor or a two-dimensional conductor or a three-dimensional conductor. And this averaging is discussed in one of the tutorials that go with week 1. Now, similarly, in the diffusive regime, where people think in terms of a conductivity, what we showed was you can obtain this expression for conductivity, which depends on this diffusion coefficient. And here again, there are 3 numbers because this involves an average of V squared. And in 1D, 2D, and 3D, the numbers are different. So it's V squared tau divided by the number of dimensions. That's 1/2 and 1/3. And then this is the density of states. And in 1 dimension is the density of states per unit length. In 2 dimensions is density of states per unit area. And in 3 dimensions is like density of states per unit volume. So those are the 3 things we have. So we have an expression for conductivity, an expression for the ballistic conductance, and you can express the conductivity in terms of the ballistic conductance times the mean free path. These are the main results that you can look back, I believe it's module 1.5, where these expressions were obtained finally from the discussions in week 1. Now, in all of this discussion, as you can see, the density of states, I said, is kind of a given, like you know it from somewhere. And as I've mentioned before, usually the way you know it is from experiments where people do all kinds of like photo emission experiments and optical absorption experiments to get an idea of what these states are. And there are models that people use, which we didn't discuss at all in week 1. We said that, well, let's say we are given a density of states. Question is, what is the current flow? What is the conductance? And we obtained these expressions. Now, our objective this week is to introduce what you might call the simplest model for this density of states. And this is the model that will more or less be what we'll be using for this course. In other words, like there's a second course, as you know, another 5-week course where we go into more detail into the quantum models. But for this course, the basic model we'll be using is what I'll be discussing this week. See? Okay. So the model we'll be using is based on an important observation that dates back to the early days of solid-state physics. That is, that you see, a solid is a rather complicated object. And you might say that, well, an electron moving through the solid, must be a very complex affair. And that's indeed true. But one of the important insights that people got is very early in this, like back in the 30s and 40s, is that electrons moving through a solid behave almost as if they're moving in vacuum, but with a somewhat different mass or a different energy momentum relationship. So let me explain what I mean by that a little more. See, when you have electrons in vacuum, as you know, usually you'd write the energy, electrons just have this kinetic energy which you'd write as half mv square, usually. Or actually more generally, and that's the form I'll be using, that instead of half mv square, we'll use this p square over 2m, where usually, yes, with this p stands for momentum, that is mv. So here, of course, those two are equal. You could show easily that if p is equal to mv, those two are really the same thing. But in general, as we'll discuss, there can be more general energy momentum relations where this one may not be quite right, but this still is. So this is the one that we'll be working with. And usually people write E equals, say, p squared over 2m. And this is in vacuum, where this m then would be what we call the free electron mass. And one of the very important insights in solid-state physics was that even in complicated solids, let's say like silicon, gallium arsenide, where electrons are moving through this complicated object, it behaves in the energy range of interest as if there's an energy momentum relation like this, but with a somewhat different mass, which people call the effective mass. And one might add a potential energy to it, a constant EC. So this would describe electrons in many of the common semiconductors. But actually energy momentum relations could be more complicated than that, because these days, for example, one of the more very popular materials on which there's a lot of work, both basic and applied, is graphene. And in graphene, E is actually linear with momentum. So it is there as if there's a constant times P. So in that case, you cannot quite visualize it as in terms of a mass. But the point is there is this energy momentum relation. It's well known. Now we'll use this energy momentum relation as a starting point. So we'll say that, well, from various sources, experiments, theory, we know that in this material, we have a certain energy momentum relation, which could be this or this. And the question is, how do I obtain the density of states from a knowledge of this energy momentum relation? That's basically what we'll be talking about this week. Now, the way it works is, way we'll do this is, we'll first define something that we'll call, let me name it, N of P. This function, what it stands for is the total number of states that you have whose momentum happens to be less than P. So let's think of a two-dimensional conductor, say. Just to be simple. So let's say I've got a two-dimensional conductor. So momentum can have an X component and momentum could have a Y component. And if I draw a circle like this, that tells you the magnitude of the momentum. And momentum minimum, it could be 0, and then it could be something more than that. And this N of P tells you how many electronic states are available up to this radius. Now, this requires some discussion because you first have to argue that how are these states located? And that is a discussion we'll go into in the next module. But one thing you can expect without too much thinking is that if you're talking about a two-dimensional conductor, then this function n of p should depend on p squared. Why? Because if it's two dimensions, then you see the area of this circle is pi times p squared. So this should be, so the area available is proportional to p squared. So if you assume that the states are uniformly distributed in here, then the total number of states you have should be proportional to p squared. Of course, exactly what constant goes in front, that's what we'll do in the next module. So for the moment, we just note that n of p is proportional to p squared if it's two dimensions. It is, what if it is three dimensions? Well, then I should be looking at the volume of a cube. And that would then be p cubed. Or if it's one dimension, then we're just looking at a line. So it's just proportional to p. So in general, I could write n of p is proportional to p to the power d, d being the number of dimensions we are interested in. Okay. So first step then, in terms of finding density of states, is to write down this function, which, as I said, without going into much detail, we can see it should be proportional to p to the power d. Exactly what constant is in front, that's what we'll talk a little more in the next module. Now, but let's just talk about, well, even if we had this, what would we do with it? Well, the procedure is that we have n of p. Next step is we know the energy momentum relation from somewhere. So if it's graphene, it's this one. If it's silicon, it looks like this. So these are all different energy momentum relations. And what we'll do is combine n of p with this E of p. So in general, we have some energy momentum relation. So we can combine those two things to obtain a n of E. Let me take this off.